Okay, so today we are going to talk about logic gates. So this is the fundamental building block of all the digital circuits. So that's why we are talking about this. So I know this you have discussed about this in your secondary school. So that may be not very difficult to you. However, at the end we are quite expand in the topic. So we'll be discussing about how to develop these using only one or two gates. Okay, so that will be, I think, the new part for you. So listen carefully. So you'll be able to catch up everything at the end if you listen carefully. Okay. So if you have any questions, don't hesitate to ask me. So logic gates. So at the beginning, I should mention why we discuss about this. Again, I should highlight that it is the fundamental building blocks of the digital circuit. So that's why we are discussing about that. So what is a logic gate? It's actually an electronic circuit which performs a logic operation. In other terms, a Boolean operation. So, okay, so it's called a logic gate. So, so why do we study about logic gates? Again, because logical functions are used in when explaining how digital circuits work. Okay. So they are implemented by interconnection of a set of gates. So you know the basic logic gates we have always learned in other like physics in advanced level also. So there are basic logic gates mentioned in this slide, as you can see. This is the AND gate, this is the OR gate, and this is the NOT gate, which are the basic logic gates which we use when drawing these logic expressions. So these gates has two or more inputs and sometimes one input. Like as an example, this NOT gate is actually only one input. It would get the complement of the whatever the input you have given to that gate. And these are the two input AND gates. So you can see the AND of the two variables as the output. And this is the OR gates, and you can see the OR of the two variables at the result side. So, so the corresponding truth tables are given in the right hand side. As you can see, A, B are the inputs. So there are 4 input combinations, the possible input combinations. So when the AND operator is applied, you can see the 0, 0 is 0 and only 1, 1 is 1. Mainly because ANDing required both to be considered. Okay, A and B. Also that if you look at the English meaning also, A and B both need to be true to have a truth in the right hand side. So or is as the English term means either A or B can be 1, then the output will be 1. And in the complement you can see whatever the input value is given, you'll get the complement of that value. So O and gates with more than 2 inputs also can be defined like this. Okay, A, B, and C are the inputs. So this is the corresponding output if you write. And these are the corresponding truth tables. So which there also you have to consider ANDing is only true or get the value 1 when all the variables has the values 1. So ORing, if you see, it can become true if one of the variable A, B, and C becomes true. Okay, so that's the condition there. So let's proceed. So those are the basic logic gates, A, O, and then NOT. So apart from that, we study the other logic gates, which are actually modified forms of the basic logic gates. So this is NAND. So NAND means not AND. So you can see you get the complement of the AND operation. And NOR is not OR. So here you can see you get the complement of the OR operation. And if you look at the right hand side, you can see the opposite values you got from for the OR in operation here. So and if you see, look at the right hand side of this function, this truth table, you'll see the opposite of the values you obtain here. Okay, so here. So those are not and then not or gates, and look at the symbol. So in AND operation and gate, we have the shape as this, which resembles D here. Okay, so it's quite easy to remember in that way. And the OR gate D here like this. OR gate you get something like this instead of this. Okay, so and it's easier to remember this dot from D for dot, something like that. So that's something else from out of the scope of our discussion here. So in this NAND, so it's not AND, and no, it's not OR. Okay, so these are the truth tables available, corresponding truth tables available in this side. Okay, so so here you can see, so in NAND actually it's equivalent to this AND gate and the NOT gate. When these are combined together, this NAND gate is formed. And this side also, this NOT gate, when combined with this OR gate, you will get this corresponding NOR gate. So, so another, actually this is a modification. You can see here is we have added the XOR, X in front of OR gate, and this is the X NOR gate, and there you can see the in the symbols, it's symbolized by having a single line in front of the both gates. Okay, so there are the specialities. So if you consider this and A O B, you can see so this gets 0 and the last combination also is 0. So these two are similar, this 2 and this one is similar. So this is only different in XOR gate. So 1-1 input combination, when you see the 1-1 input combination, you get 1 in A and B, however, not of that in XOR. In XNOR also, you can see if you compare OR in of not OR like this. So what's the difference? You can see so you can see 0 here instead of 0. You can see 1 in this XNOR gate. Okay, so so those are the basic types of gates we discuss in this course. So apart from this, so with this information, we can actually draw now logic gates using these gates. Okay, so now you know the basic logic gates, and they are modified forms and some other logic gates created by modifying the OR and gates. So here when you are drawing a logic circuit, so when you are provided with a Boolean expression, we can draw a logic circuit in this way. So, so this is an 3-input AND gate and operation. So for that, you can use 3-input AND gate, and the last term is primed, you can see. So to get the complement, you can use an NOT gate like this. Okay, and so the other gates for AB plus C or A and B or C. So then you can see a single gate for to represent this A and B, this one specifically, and C in the other side uh, by ORing the output of A and B and C. Okay, so you will get the final expression like this. And in the third expression, when I representing that in the right hand side, you can see ORin of A, OB and dot C. So here you can see you get ANDing of, sorry, ORin of A and B. So you can use a OR gate for that purpose. Okay. So that after that, here it's AND with C, so you can get the AND gate and get the ANDing of A, O, B, and C. Okay, so that's what we can do. So that's how we can represent these three. This is the first one, and this is the second one, and this is the third one. Okay. So this is how we can draw logic circuits for a given Boolean expression. So these are very basic expressions. So now you can draw a logic circuit for this given expression. I'll give you some time and let's see the answer next. Okay, so that this should be the answer for the given Boolean function. So this is how you can draw the logic circuit for the given Boolean expression. So to get the complement, you can see you have used an NOT gate here before giving the input into this 3 input AND gate. So you can go for 3 inputs for OR and not apart from the NOT gate. For other gates, you can go for 3 inputs. So not more than 3 inputs you can go actually. So it's not good to go more than 3 inputs. When you're drawing, keep that in mind. Okay. So here you can see you have used 2 NOT gates because you can see this is prime. So the complement of this can be represented by using a NOT gate here. So next you have to draw the logic circuit of this Boolean expression. For that you have to first simplify F using positive defs and theorems or K-map, then draw the logic circuit of simplified F. Okay. So So that so you can write, I will upload the slides so you can see this, and let's keep this for the moment. You can do it as homework, or let's do it if time left at the end, because today we have missed some time. So here, now we are going to look at how we can analyze a logic circuit. So given a logic circuit, one can write the corresponding Boolean function looking at the circuit itself. So, so if you can, we can apply all the possible input signals to this and write down the equation. So can you try it? So there are three inputs, A, B, and C, and A and B are actually not gate is applied. So soon after its input, so you can see in this output as A dash and B dash, and here A dash and B dash are have applied AND operation. So we'll write A dash and B dash, and you get C and A dash and B dash input into this O gate. So you get A dash C O A dash dot B dash, and then you have get the NOT of this operation, C O A dash dot B dash, okay, and get the complement of that. So that will be the function f, which is represented by this Boolean circuit, logic circuit, okay. Okay, so that is what we have done. So you can simplify this into this form using the De Morgan's theorems. So, so that's how basic logic gates and about basic functions we can do, associated basic functions we can do with logic gates. So here, now we are talking about the universality of NAND and NOR gates. So what is universality? So, so that's actually in other terms, we can implement any logic expression using only NAND gates and no other type of gate. So this is because you can see if you get this corresponding input combination, so you can see the same input A is given to the both inputs A, okay. So so in NAND gates you can actually draw all the three basic gates using only NAND gates. So that's why we call it's universal. O gates or NOR gates also it's the same, okay. First let's consider this topic, universality of NAND gates. So it means it's possible to implement any logic expression using only NAND gates, okay, no other type of gates required. So if you look at this side, you can see how all the three basic gates can be implemented. It means if the basic gates can be implemented logically, should be true that any logic expression should be able to represented by these NAND gates only. So instead of using many gates, using a single type of gate, we can represent any given Boolean expression, okay. So that's the basis. So to prove that prove the universality of NAND gates, we can draw the figures on the right hand side, which represents that you can draw all the basic three logic gates using NAND gates only, okay. So that is actually proven on the right hand side. So if you look at the NOT gate, it is represented by a NAND gate here. To prove that, you have you can give both inputs same value to the both inputs, and you will get as the output the complement of that input. Okay, you can see how it happens and why it happens from this side. So A is multiplied by A, not multiplied this actually. This is the AND gate, AND of A and A's complement is the output of NAND gate. So when you give the same input, you can see that you get the complement of A. So that is equivalent to inverter or the NOT gate. So if you want to draw the AND gate, you can draw something like this, okay, one after the other. So the output of one NAND gate is input to the second NAND gate. So you can see the complement of the first combination is given to the second NAND gate, so which is complemented again. So you will get the required result at the end. Okay. So so that's the output there. And if you look at the OR gate, OB is represented by, it can be represented by a circuit like this. Okay, so there, to represent the O, you can get the output of two NAND gates and input to a single NAND gate. So there you can see you get A dash B dash complement at the end. So this is equivalent to AOB, mainly because, so if you apply the De Morgan's theorem here, so you can see A dash B dash its complement equals to A dash dash, this AND in is opposite, we get O if we see AND, B dash dash. This is according to De Morgan's theorem. So if you look at the De Morgan's theorem, this is true. In its one term's complement can be written as, so if it's AND in, you can write this as a O ring where the terms are complemented. Okay, so that's a De Morgan's theorem. So A dash dash equals to A and B dash dash equals to B. So this is the final solution you get. So by having three NAND gates, we can represent OR gates also. So what did we look at here? We looked at how the basic three logic gates also can be represented using only NAND gates. Here in the figure 1, it shows you that NOT gate can be represented using a single NAND gate. And in the second figure, it shows you that AND gate can be represented using two NANDs. Okay, and here it shows you the OR gate can be represented using three NAND gates. So this shows the universality of NAND gates. It means that we can implement any circuits using only NAND gates. We don't need the other three types of gates because we can implement those gates using these NAND gates only. Okay, so that's the basis. So, so similarly, we can show that you can NOR gates is also universal. So to prove that, what you have to do is you have to show that all the three basic logic gates can be drawn with using only NOR gates. Okay, so that should be the that you can use as the proof. So in a similar manner, it can be shown that NOR gates can be arranged to implement any combination of any Boolean operation. So here you can see it shows and NOT gate and OR gate and AND gate are represented using only not NOR gates. Okay, so this is a NOT gate, this is OR gate, AND gate. So all the three can be represented using NOR gates, similarly as we have done with NAND gates. Okay, so here to represent a NOT gate, so you have got the again you have input the same variable into the two inputs, and at the end you will get something like this. So because A O A's complement is equal to A's complement. Okay. So secondly, if you look at this, so you have used two gates and one after the other. So these are actually NOR gates. So you get the OR in of A and B, and it's dash because it's not form of that gate is given get here. We get here. So after that we input both at the same time to the two inputs. So at the end we'll get as the output A, O, B as the output. Okay. So because we get, you can see here we get the complement of this input, and you get this which is correspond to the OR gate output correspond to the OR gate. So thirdly, so you can see the AND gate which is being represented with three NAND gates. So here you can see A's complement and B's complement can be created by using by inputting the same input to the two inputs. So lately, so you can input both A dash and B dash into a single NOR gate and get the output as this. Okay, so that is the main output of a NOR gate. So so now we are going to look at, so we now proved that we can implement any logic gate using only NAND gates or only NOR gates. Okay, so our first target here is to look at how we can develop Boolean expressions using only NAND gates. Okay, so that's our main target now. So first we had to obtain the sum of products form of Boolean expression given. So this is the Boolean expression provided. So it's already in the sum of products form. So you can see products and it's in the sum of products form. So then you can use De Morgan's theorem to obtain expression using two-level NAND gates. Okay. So so this De Morgan's theorem is really helpful. So you can see here. So F is, first you have to consider this. So F is equals to if complements complement. It does not change the value in the left hand side by taking the complements complement. Okay. So you apply it here. So F equals to this value. So these values, we get these values complements complement. Okay. So that's equivalent to this expression here. So then after that, so we apply the De Morgan's theorem. So to term by term, and then you will end up by having this. Okay. So you get, so if I write it here, x y dash plus x dash z. Okay. It's complement. So look at the inner complement, and we can apply De Morgan's theorem looking at this expression. Okay. So it's now x dot y dash dot x dash dot z, it's dash. Again, you have to consider the outer complement and keep it here. Okay, so this is what we have. We can see here. So then now you can see. Now you can see we have applied De Morgan's theorem and come up with something like this. And now you can draw the circuit using only NAND gates, because you can see here this is a set of NAND gates. Actually two NAND gates if you consider. So x y dash NAND of that, and x dash z is NAND of that. Okay. When you input this both to a single NAND gate, so you will get the complement of that both product. So you have products here. Here product, here again a product, and here again a product, and complement of these two products and the whole product. Okay, so that's why you can represent these two terms in using NAND gates only. Okay, so when you represent in NAND gates, it should be a AND in and complement of AND in. Okay, should be a complement of AND in and should be a complement of AND in. So do you get what I say? So these are important. So to represent the final two terms, complement. So let me erase this. So to be represented by a NAND gate, what are the requirements? So this is the NAND gate. Okay. So if I input A and B, what's the output? A dot B is complement. Okay. You have to form this equation into this form. Now is it in this form? This one? This one is not in this form because we don't have a outer complement mark here. So to convert that into that form, we get complements, and then you end up with having something like this. If you consider this equation, what is A, what is B? A is this. Okay, B is this. Okay, the complement mark is here. So again, you have to see whether you can represent these two terms using NAND gates only. And here what is A? X is A. What is B? X dash, Y dash is B. What is the complement? Is there a complement? Yes, there's a complement. Okay, so likewise, you have to analyze. And you can see now you have come up with the equation. It can be represented only by NAND gates. So here also this is not represented only by NAND gates because these inputs also need to be expanded. Okay, so here you can see Y's complement is taken by having a single NAND gate and input in Y into both inputs. Okay, and X complement is taken by taking X and giving the same value for the two inputs of the NAND gate. Okay, so lately you can input both these into this NAND gate and you will get the corresponding equation. Is it clear to you now? Okay, now let's go how you can implement using NOR gates only. Okay. Okay. So when you are implementing using NOR gates, so the procedure is you have to obtain product of sums form. So if you compare this one, when you implement using a NAND gate, you have to write it as a sum of products form. It's mainly because you can see here, so these terms can be formed if you only start with this, because when you apply De Morgan's theorem, the things change. So that's why we need to represent this as sum of product form here and product of sums form here. Sorry, here. Okay. Product of sums form here. So here you are given with an equation. So then to obtain product of sums form, so here the equation given itself is in the product of sums form. So we don't have to do anything here. And we have discussed that how we can represent any equation as a product of sums form in the previous lecture. So you can have a look at that. And now or canonical forms, when you're talking about canonical forms in the previous lecture, we discussed that. Okay. Now we are going to use De Morgan's theorem to obtain expressions using two-level NOR gates. So this is the representation of the product of sums from of the given Boolean expression. So after that again we apply complements complement. So F equals F's complements complement. Okay. So when we apply this one, what we do is we get the complements complement, and again then we apply the De Morgan's theorem. So you can see these terms are now complemented. So let's write it here. Okay, so then you sorry. You have to get the complements complement here. Okay, complements complement like this. So then you can apply the De Morgan's theorem. So when you apply the De Morgan's theorem, so this is a and here, and in is here. So what you can do is you can get the complement of the terms and then convert this into a O mark. So this complement of this. Now have you written this in the form which can be represented using NOR gates? Check whether you can represent this using NOR gates. NOR is the not O of two inputs. So this is equal to this. Okay, this is equal to this. So let me clear up this part so that I can explain whether now we have represented this in the form of NOR gates. In the form which you can represent it using NOR gates, okay? Okay, what is NOR gate of A and B? A, O, B is not. Now, is this in the form of A, O, B complement of that? What is A? A is this. Sorry, this whole term. Okay. So this whole term is A now. Okay. This whole term is B now. So after that, where's the complement? Complement is here, you can see. So after that, you have to check whether this term, whether it can be represented by using NOR gates. So in that term, what is A? A is this. What is B? This whole term is B. And it is complemented. So it can be represented only using NOR gates, okay? So how can you do that? You can draw a circuit like this. So you can start from this end and then represent the two terms as the inputs. So how can we represent this? Again, the inputs terms are x and y dash, and they are input to this NOR gate. Okay. So again, if you look at this x dash and y dash cannot be kept in this form because inputs should be either inputs should not be in complemented form. So then you can implement this a dash and x dash and y dash using NOR gates. Okay, so that's the next step. So that's not drawn here. So you can extend this diagram like this. X, okay, something like this. You can expand drawing like this. So this should be your final answer. So first you had to realize the logic expression given here using basic logic gates only. So when you're drawing this, first you had to use only basic logic gates and then implement the circuit using NAND gates only. So I'll give you a few minutes so you can draw that. Okay, so these are the possible answers. So this you need to expand. So you can first draw this and then expand. So this is using only the basic gates, okay? And then the next question, using only NAND gates. First you have to so check whether this is in the form of sum of products. So yes, this is in the sum of product form. So then what you have to do is then use if however our main target is to apply a De Morgan's theorem. So I'm just using this which does not harm the meaning of that in this form, okay? And then you have to get the complement expanded by using De Morgan's theorem. So the answer would be something like this. Can this be represented by a by NAND gates? So you have to check that. And this you can represent by a only NAND gates. So there's exercise. So that's what I have planned to discuss on that topic. Okay. Okay. Can you see the slide? Now, I think you can answer this question. 4. Design a logic circuit to implement the complement of f in simplified sum of products expression of the simplified sum of products expression obtained in 3 by using non gates. No gates. Clearly indicate the method and steps you follow.